This is Math 432, Applied Combinatorics. I'm Professor Asaph, and today we're talking about permutations. So what I mean by a permutation of n is going to be a function. In fact, it's a bijective map. It's a bijective map. And since it's on n, we're going to say from the numbers 1 to up to n to itself. So there are lots of different ways for us to visualize permutations of n. One is to think of them just in terms of this definition. We have the domain, 1, 2, 3, 4, 5, 6, seems to be good. And we have the range, 1, 2, 3, 4, 5, 6. Now we need to make a map. That's going to be a correspondence. So we have to decide where everything goes. So 1 maybe goes down here to 5. Seems like a perfectly reasonable choice. 2 can maybe go up to 1. It couldn't go to 5 because I said I want a bijective map. So there were 6 choices for the number 1, but only 5 choices for the number 2. 3 has 4 choices. The number 4 has 1, 2, 3 choices. Maybe we'll send it down here. 5 has only 2 choices. And by the time we get to 6, there's no choice left. It has to go to whatever remains. So theorem, there are n factorial permutations of n. So there are different ways we can think about these. The way we've done it here, we've sort of thought of them as a linear order. Well, we thought of them as a map, but we can think of them as a linear order. So a common way to write down a permutation instead of going in this cumbersome way is just to start with the numbers 1 up to 6 in some order, and then say, okay, well, where do I map 1 to? And we'll put that number right below. So looking here, I map 1 to 5. Okay, and then where does 2 go? 2 goes to 1. 3 goes to 3. 4 goes to 6, 5 goes to 2, and 6 goes to 4. So if I write it like this, then I've written the permutation in what's called two-line notation. The top line will always be the numbers 1 up to n, and the bottom line will be the numbers 1 to n in some order. In fact, it's in a linear order, which is how we can see that, again, we get the number of linear orders. And you can see from two-line notation that the top line is somewhat redundant, right? We already know that the numbers 1 to n show up in the top line, so it's fine to list a permutation in one-line notation. One-line notation is a perfectly good way to do it. There's another way that we could do permutation, which is called cycle notation. Cycle notation is, again, thinking of it more as a map rather than in one line. So here's how we're going to do cycle notation. So this is an important notation for permutations. If I take this example here written in one-line notation, I can recall that it was originally in two-line notation, and maybe that'll be helpful to put it back for just a moment. Let's see if we can bring our penguins back without too much fuss. Okay. So for cycle notation, what I'm going to do is I'm going to start with the number 1. Where does the number 1 go? Well, the number 1 goes to 5. Okay, so we can draw it here to 5, which if I'm writing it just in terms of a cycle, well, let me do it as a map first. Where does the number 5 go? So I'm just continuing from here. I went from 1 to 5. Now where does 5 go? 5 goes to 2. So 5 goes to 2. Where does the number 2 go? 2 goes back to 1, and I've closed up my cycle. So I can write this cycle as 1, 5, 2, and that's a full cycle. But obviously I haven't used all my numbers. I've used the numbers 1, 5, and 2, so what's the smallest number I haven't used? It's 3. So where does the number 3 go? I'll look here, 3 goes to itself. That's a perfectly reasonable thing to happen. So 3 is in a cycle all by itself. The smallest number not yet discussed is the number 4. So I look here, where does the number 4 go? 4 goes to 6. Where does the number 6 go? 6 goes back to 4. And so I can write the cycle like this. I can either draw this picture, which really helps me see the map aspect of it and the cycles themselves, or I can write it just in cycle notation like this. But notice that there's some redundancy in the cycle notation, right? So I've written here 1, 5, 2 because 1 goes to 5 goes to 2, but it's also fair to say that this is the same as 5, 2, 1. This is 3, and this could easily be 4, 6. This cycle notation represents the same permutation. So one-line notation is very descriptive and very precise. If I have two numbers moved into a different position here, it's a different permutation. But in cycle notation, that's not the case. These two are actually equal. And in fact, it doesn't matter that the 3 here is in the middle. I can move the 3, say, to the beginning. And I could end up with 3 followed by 5, 2, 1, followed by 6, 4. This is another way that I could have done it. And in fact, this is an important way to do it. If I take each cycle and I think, okay, in each cycle, what's the biggest number that I see? Here, 5 is the biggest number that I see. 3 is the biggest number in this cycle. 6 is the biggest number in this cycle. Then canonical cycle notation tells me that what I must do is take the smallest of the circled numbers and put it first, and then the next biggest, and then the next biggest, always starting my cycle with the circled number. So this is what we will call canonical cycle notation. It's important because if I just wrote down 3, 5, 2, 1, 6, 4, you could recover where the parentheses are without me telling you. Whenever I see the biggest number I've seen so far, I must start a new cycle, right? So 5 starts a new cycle because it's bigger than the 3. And then 6 starts a new cycle because it's bigger than all these numbers. And those are the only two numbers that have that property as I read it. Okay? And then I know when the cycle ends and when the cycle begins, so I can exactly recover it. So this is a good way. Canonical cycle notation is a great way to get a bijection between the cycle types and the one-line or two-line description of a permutation.